I have added a subtitle because that way I wanted to lighten the burden on myself. This is because I feel that it is presumptuous to try to speak on future directions, and that too on the theoretical front, being an insignificant mortal myself. Besides, practically whatever I have to say has been said by someone or other during this meeting itself, and I have picked out only a handful of points out of whatever has been said, and this choice may be very unbalanced and it will reflect bias as well as inadequate understanding on my behalf. So people may very justifiably disagree with whatever I say. In that context, I have a suggestion that since the material that will go across is of a diffuse kind anyway, any comments or misgivings that people may have may be expressed at the end itself, where anybody can respond to everything or everybody can respond to anything being said, and we can have a sort of open house discussion that way. And also, since a full talk on experimental directions is scheduled after this, I am avoiding discussing experimental issues, which are the more important ones, as far as possible, and that will make my discussion even more constrained. Now, since the root of the future lies in the present and that of the present in the past, let's try to examine the recent or relatively recent developments in particle physics. It is often said that we have gone through a phase of stagnancy for nearly 50 years or probably a little more, even a stagnancy not relieved even by the discovery of this 125 TeV scalar. I start by asking myself, is that indeed the situation, and look at some developments in 1967. Here I may be again unwillingly leaving out some very important developments which at least my most historically minded friend here will immediately catch me for, but I apologize in advance. In 1967, we saw the Glashow-Weinberg electroweak theory in shape, and in 5 years' time, its renormalizability proven. In the late 60s, we also saw an establishment of the fact that nucleons had substructure, something that led to the development of the Parton model, QCD, quark model quark model, QCD, and finally asymptotic freedom being established in the 60s and early 70s. In the 70s, parallelly, weak neutral current was found, and several important discoveries of elementary particles took place, not to speak of the three-jet events which crucially confirmed QCD in a sense. And in the 80s, there was discovery of the W and the Z, together with the discovery of a non-vanishing value of one of the fundamental constants of nature, termed as BDK. In 1990s, the top quark was discovered, and then came the super Kamiokande results on neutrino oscillation, something which definitely gave a fillip to neutrino-related studies, and then direct CP violation in kaon decays was seen. In the 2000s, we saw nu tau being actually confirmed as a particle in the donut experiments, and CP violation in B decays, one more fundamental constant of nature found to be a finite quantity. In the meantime, in the 90s and the early 2000s, the standard model was experimentally established to be a renormalizable quantum field theory thanks to precision electroweak observables. And it is the same approach which brought important conclusions like the limit on the number of sequential fermion families, and even succeeded in giving a rather remarkably accurate mass range for the Higgs boson without the Higgs being actually seen. And of course, in 2012, a 125 GeV, almost certainly scalar particle was identified, which was at least a Higgs-like particle, if not the Higgs. In the meantime, thousands of scenarios going beyond the standard model was formulated, probably more than is healthy for the theory community. And this included a number of things on which we have had umpteen discussions in this meeting itself. On the other side, the theoretical principles of perturbative QCD was very minutely explored so that sophisticated calculational tools could be discovered or developed, and tools which could be used to predict the outcomes of high energy collider experiments in spite of the necessity of certain semi-empirical procedures which would sort of allow us to circumvent the roadblocks offered by our lack of understanding of quark confinement. Side by side, a very, very crucial development was the beginning of an interplay between particle physics, astrophysics, and cosmology, something which was buttressed by the appearance of a huge mass of astrophysical data, the development of precision cosmology, formulation of inflation, getting the dark matter issue on firm footing, and so on and so forth. Essentially, particle physicists feeling infinitely more enriched and empowered thanks to their tie-up with cosmologists. All this happened in about 50 years, and this theoretically spanned a rather massive platform and a structure, which is the standard model, ably tagged with the standard model of cosmology. Of course, there is a makeshift nature and ad hoc nature in the standard model, but I should say, at its worst, it is a pluralistic theoretical framework, and at its best, a solid platform based on which we can continue our further quests for more unified, more comprehensive, and more predictive theoretical patterns. Now, we may compare this with classical electrodynamics. Of course, not this wide and complicated crossplay was there, but Maxwell's equations were found in final shape in the literature in 1861, and for well nigh 40 to 45 years, no new physics in that direction or that line was found till a patent clerk in Bern started thinking very differently. Now, are we then, if we compare this 40-45 years in electromagnetism versus 50-ish years with the electroweak theory and QCD, if we are complaining about stagnancy, are we doing that because we have been spoiled by the first 30 years of the 20th century, which is appropriately called the 30 years that shook physics? Possibly yes, and it's also possibly true that we are frustrated because we are learning many things, but they all reinforce the same structure called the standard model, the hints for new ones being rather sparse. And also because we have probably spoken faster than we have thought and proposed many options beyond the standard model, which has made us increasingly more impetuous about new physics with scanty experimental results. Now, of course, we can't help that, and we have to have our future directions based on whatever scanty leads we have got so far. And here are my personal bias for a bottom-up approach is what I'll base this discussion on, without at all denying the merit of certain top-down things which at least give us some theoretical insight about structures. Now, in this approach, the observations that concretely and persistently imply going beyond the standard model are quite a few. Dark matter is the foremost among them, neutrino masses and mixing, of course, baryon asymmetry, perhaps dark energy, whether it is inadequacy of standard model or it's a kind of inadequacy of our understanding of gravity, we have to sort out that. But in this talk, I'll mostly discuss directions of thinking related to the first two of them, and make only passing reference to the remaining two. That's largely because of lack of time, and very importantly because these are such potent and important issues that not having actually worked on them much, I am very hesitant to make statements about future directions. Before we take these two, let's start with the Higgs, the most recent toy which has been gifted to us by Mother Nature, and where we know, based on the LHC data and other precision data, which, for example, the Tevatron has handed us out, we know that the signal strengths of the Higgs produced and decaying in various channels is by and large consistent with what the standard model predicts at 2 sigma level or even more closely. However, just as a glass that is half full can be looked upon as half empty at the same time, there remains scope for departure from standard model interactions up to a certain level, and one will never cease to be intrigued or rather excited by the possibility of such departure. More uncertainty, of course, are those final states where there are fermion couplings involved. For obvious reasons, there is experimental uncertainty, and also little clue on possible CP violating nature of, for example, the HBB bar coupling. This lack of information or kind of a problem of finding proper variables to see CP violation in HBB bar coupling is largely due to the fact that the B quark hadronizes, and the hadronized forms don't retain polarization information of the B, excepting this baryon called lambda B, which does carry polarization information. But lambda B branching ratios too are not well known experimentally, and there are some difficulties in calculating the fragmentation function of lambda B as well. So this is one epic example of a situation where a kind of serious theoretical issue is kind of jumbled up in a quagmire of experimental problems. Now, also invisible branching ratio of the Higgs up to 10 to 15% is definitely allowed. When the ATV run came to a close, Atlas paper officially allowed something like 23%. I am being conservative and saying any scenario that leads to 10 to 15% Higgs branching ratio is definitely consistent with the present data, and this is definitely a tantalizing factor to those who are in the lookout for dark matter. Now, departure of the Higgs boson departure from standard model coupling of the Higgs can be of two kinds. The coupling strengths being just scaled by a multiplicative factor with respect to the standard model values, or different Lorentz structures coming into play, even with small terms. And such structures often come from higher dimensional operators, which smack of an effective theory encapsulating the existence of new physics that could be beyond our reach. And these Lorentz structures different, mind you, they may affect the momentum dependence of the Higgs couplings, though in a small quantity, and they may affect the efficiency of cuts applied in the collider to separate the signal from background. When it is scale couplings, it may mean either the Higgs or the particles to which it's coupling, like 2 Ws, 2 Zs, 2 fermions and whatnot, they are mixed with something unknown. And this immediately opens avenues to think of new physics which can be accessible to direct search as well, because in order for the coupling to be, mixture to be finite, you normally expect the new particles also to be within your reach. I emphasize this is a wishful thinking, but this is a way of thinking. When it's different Lorentz structures, which if they at all manifest themselves, for example, in the high energy run or even the high luminosity run, then they may signify new physics which is beyond the reach of the LHC, but which is integrated out to give new Lorentz structure. Therefore, effective field theory approach to understand the effect of them takes an important turn and becomes probably our most useful tool. One may think of in terms of some symmetry of the new terms, thinking of criteria which are set down already by effective field theorists to distinguish between free level and loop induced effective interactions from their magnitudes and very other observables. And there are many other things that can come our way. Now, a wealth of information can come, and is probably the most important thing to tell us whether it is the Higgs or a Higgs is the self-interaction of the boson. If it exactly is something like 0.129 or whatever is the value predicted in the standard model, or very close to that, then we will be very strongly convinced that we are looking at the Higgs, which has but little departure in its property from whatever the standard model tells us. However, the LHC has rather poor insensitivity to lambda, unless its lambda is very Higgs, and di-Higgs productions and similar things can hardly explore it for the kind of values we are talking about. And unlike what is normally thought, an E plus E minus machine, according to various TDRs, cannot probe the self-coupling of the Higgs to accuracy or precision more than something like 15%. And it is very difficult to imagine at any rate that even if there is new physics in the Higgs sector or new physics in the Higgs self-coupling sector, it will be a departure by something more than 15%. History normally doesn't teach us that way. Does it mean a no-go is a big question. So can't we think of ways, theoreticians, not experimentalists, whereby the self-coupling of the Higgs can be probed more effectively? For example, the di-Higgs data, which finally will yield supposedly information on the self-coupling, is the predicted contribution is lowered because of a destructive interference in Feynman diagrams involving TT bar H coupling. Now, can the combined data on di-Higgs and TT bar H, however sparse, tell us something new? Is a big question that one doesn't know. And it will, of course, be a great achievement to formulate some novel effects or novel observables, much in the line of the oblique parameters in the lab days, which could yield precision information on lambda, something which has not been thought about, but something which will be a great service to our entire effort. Then comes the issue of vacuum stability in the Higgs context, and this figure, of course, was shown in John Ellis's talk. But essentially, the problem is that if the top quark mass is not below something like 3 sigma below its central value of experimental value, the pole mass, then the self-coupling theoretically turns negative at somewhat high scales. The result is at best a metastable vacuum. So if standard model has to be true, and there is nothing but the standard model all the way to the high scales, then probably we are living in a metastable vacuum. Now, of course, there is no clear guideline on what kind of new physics can restore our stability at high scale. Of course, you can think of 100 things starting from various, even high-scale broken supersymmetry to gut to whatnot, but it remains at the level of speculation. But in contrast, people have thought of many kinds of new physics scenarios at low scale itself to do it. Here, the issue is that the lambda turns negative due to fermionic or Yukawa coupling contributions to the renormalization group equations. So, the addition of bosonic degrees of freedom will offset this effect and try to restore the positivity of lambda. The hazard being that many of the many of the readily applied or appealing theoretical scenarios doing this will raise some self-coupling of one scalar or the other to such value that perturbativity will be threatened. Of course, there are examples where the balance can be struck. For example, in two Higgs doublet scenarios, you can have stable vacuum as well as perturbative unitarity and all other good features intact, all the way up to Planck mass over substantial regions of the parameter space. Questions arise from this as to whether, in this fashion, low-scale observables, the issue of vacuum stability and related issues can at all develop guidelines on high-scale physics, which is hiding out for us, but which normally, which may have a lot to tell us about the ultraviolet completion of our ultimate theory. And the last thing that I want to mention is the question as to whether a stable vacuum is at all preferable to a metastable vacuum. Can one think of any decidedly important criterion which tells us that no, a stable vacuum is better? How do we know whether we are living in an unstable vacuum and what problem it comes to so long as the tunneling probability or the lifetime of the unstable vacuum through tunneling exceeds the lifetime of the universe? Some of the theoretical questions that arise in this connection will ultimately have to settle this issue in the decade to come. Then, of course, as I said, when I had a checklist on the Higgs boson, that it is a fundamental particle, one can ask this question. We know that Technicolor was an attempt in this direction, but Technicolor essentially wanted the compositeness scale to be the electroweak symmetry breaking scale itself. There, apart from the most contrived versions, such models normally don't survive, thanks to precision electroweak observables. Now there are new composite scenarios being developed where you don't have don't have the electroweak symmetry breaking scale as the compositeness scale, but a higher scale does that, where a higher gauge global symmetry group breaks into some smaller group, and that way one would have a Goldstone boson. If this global symmetry is an approximate symmetry, you will instead have a pseudo Goldstone boson, which may normally serve as our Higgs boson. Of course, there have been other speculations as such scenarios, composite scenarios, treated as duals of gauge Higgs unified models in warped extra dimensions of the Randall-Sundram kind. There are many implications of this which need to be fully understood. For example, when it comes to a warp geometry scenario, you cannot normally avoid, because it's a geometry and geometry brings in gravity, you cannot avoid the possibility of graviton Kaluza-Klein modes, which lead to, say, dilepton final states. And the question remains as to whether this bump hunting exercise at LHC, if this bump hunting exercise doesn't reveal any new resonance of this kind up to high scale, whether that will be a deterrent against composite scenarios of this kind. Similarly, in such scenarios, dark matter candidature has been also advocated by suggesting not exactly Z2 type symmetries, but certain exchange symmetries whose implication also need to be finally understood, since we are all worried about dark matter. And the compositeness scale, about that in such scenarios, including the little Higgs type ones, it is not at all clear whether they are stable against quadratic corrections beyond the one loop or beyond two loops. Something which is obvious in supersymmetry is not obvious in this case. And therefore, there is this issue of stability of the compositeness scale, because there is a tug of war between precision limits, which tend to make lambda large, and another hierarchy problem, little or slightly big hierarchy problem. Whether the stability issue of the compositeness scale survives this tug of war and gives us something meaningful and tangible is a question that is for the near future to answer. Next, I talk to news from the news, something that has been bothering us for decades, namely non-vanishing neutrino mass and a very different mixing pattern. Here, many of our colleagues ask the question as to whether just the existence of neutrino mass means something new. That is to say, does it mean that suppose if I have just Dirac neutrinos, it will mean something drastically different. Why? In a sense, probably it is new physics, because if there is a Dirac mass, nu r's, then no symmetry in the standard model prohibits Majorana masses involving nu r. So if there is no Majorana mass, that will mean some physical principle prohibiting them, for which you go beyond the standard model. And if there is Majorana mass, then that will obviously be lepton number violation and going beyond the standard model in the pristine form. And besides, of course, a very different mixing pattern remains our problem, and associated issues come, namely sterile neutrinos, the possibility of their existence, likelihood of new CP violet phases, and so on, not to speak of messages from the early universe, galactic activities leading to high energy neutrinos, and so on and so forth. Various mass generation mechanisms may address some of the issues, but the goal, I think, is to integrate neutrino mass models to the bigger canvas of particle physics, where we are looking at new physics scenario in other sectors as well, in particular in the lepton sector, where this bi-large mixing pattern will have serious implications on lepton flavor violation issues which are well established, well probed, but probably keep room for further modeling and investigation, particularly in terms of observable quantity. The seesaw models, of course, constitute a much used pasture, but still some greenery remains there, which will be kept alive by issues such as leptogenesis, SUSY, and so on and so forth, and also from more mundane issues like, for example, the type 2 or type 3 seesaw scenarios necessitate the existence of new scalars or new fermions belonging to unorthodox representations of the SU2 and their related consequences at the LHC. For example, there are observations like in type 1 seesaw, if it is a gut-inspired scenario, then one neutrino mass eigenvalue can be related to the top mass in this way. The question is how to verify the high-scale root of, say, type 1 seesaw, something which will have immediate repercussion on the candidature of neutrino masses, delta L equal to 2 masses in the process of leptogenesis. Now, if Majorana mass is confirmed, one may ask the question as to whether one can disentangle the 3 seesaw mechanisms, for which there are some trivial answers, but the issue is whether we have deeper ones. Similarly, CP violating phases, octant information, mass hierarchy measurement, something which is being really probed deep and dry, particularly in several experiments, whether they can establish some connection between neutrinos and the overall canvas of the physics. Absolute values of the neutrino masses is a similarly intriguing question, where some guideline comes from issues ranging from tritium beta decay to CMBR anisotropy, and neutrino factories are another one. Here I have an observation to make, namely whether there is enough seriousness given to near detector data where you can explore non-oscillation physics, which can lead to very useful constraints and probably signals of scenarios where, for example, lepton number is violated not by 2 units but by 1 unit. I don't think it has that much effect on oscillation physics all the time, but non-oscillation physics will lead to observables there. Questions remain, like, for example, whether additional scalars invoked in seesaw can lead to additional constraints on the entire mechanism due to issues like vacuum stability. Then, if there is no evidence of lepton number violation even in the neutrino sector whatsoever, will seesaw become an ineffectual mechanism? Actually, there have been scenarios proposed where with certain additional scalars and so on, you can generate Dirac masses through the seesaw mechanism. Of course, such theories are blessed with certain Z2 assumptions and so on. Whether they come naturally or look contrived is a question for the posterity to decide. But the very issue that a small mass is generated out of large mass says the essence of seesaw mechanism that actually has been shown to work in Dirac neutrino scenarios as well. Then these issues related to lepton flavor violation I have already mentioned. So instead, let me next go to one of the most pressing problems of the day, namely dark matters, and that's where we have assembled here to be enlightened by these dark candles. So it is no wonder that most of the beyond standard model scenarios that we talk about today, among them, those which offer some dark matter candidates, unconsciously or consciously get some priority, and for very good reasons. There are many examples. Most of the scenarios containing dark matter candidates are constrained by things like relic density, direct search results, indirect evidences, Big Bang nucleosynthesis issue, and so on, and also by the collider data on missing energy. However, all these constraints can be either bypassed or modified in certain conditions. For example, direct search results are quite understandably be evaded by, for example, gravitino dark matter or right chiral neutrino dark matter, or in cases where the dark matter candidate undergoes an inelastic scattering by default at the detector. This, for example, happens in inner doublet scenarios where the scalar and the pseudo-scalar have their masses split. Similarly, for all of these, some counter example can be cited. So keeping track of them is an important thing from a theoretical point of view as well. Also, not so, what should I say, theoretically potent issues, but issues which are extremely important from a technical point of view are unavoidable if we want to probe dark matter theory and try to improve or pinpoint our investigation of dark matter. These include issues, for example, like the strange quark content of the nucleon at very low energy, nuclear response in various materials which constitute our dark matter detectors, invisible mass reconstruction techniques at colliders, where considerable progress has been made, but much more is to be desired. But in some strange cases, really, the existing variables don't work. And of course, issues like dark matter profiles in the various galaxies where we are looking for them, possibility of non-Maxwellian distributions, and so on and so forth. Now, there are a few more observations. As the hints come from time to time in dark matter evidences, in direct searches, almost all data coming so far have shown excesses for various different values of xi. Is this due to the technical problems that I had listed in the previous slide, or due to something more genuine, is something which is unanswered, and side by side with improving the experiments, looking at them from the theoretical angle is extremely important if we really want to understand the issues. Some points that deserve serious thought in the near future are the possibilities of multi-component dark matter, asymmetric dark matter, thermal and non-thermal dark matter candidates coexisting, and also issues like how much importance to accord to the WIMP miracle, particularly in view of cases where warm dark matter is kept alive as a possibility. And of course, all implications of composite dark matter, solitonic dark matter, Bose-Einstein candidate, Bose-Einstein condensates at dark matter candidates, and so on. I'm sure in the coming decade we will know a lot more about them. In scenarios like supersymmetry, for example, it can be that the axino and the gravitino act as dark matter together. It is possible that not only right chiral neutrino, but also left chiral neutrino, I emphasize, can be a dark matter candidate in cases in spite of the direct search constraints being there. So such unorthodox scenarios, as well as their ultraviolet completion, will lead to useful understanding of the whole gamut of fundamental physics. For example, non-thermal Wright's neutrino dark matter, if right-handed neutrinos are there in supersymmetry, can still allow minimal supergravity-based CMSSM, something which is practically discredited these days, to be revived because the mass limits come down considerably because of a number of observations. So M-Sugra-like ultraviolet completion may get an additional boost as a result of this scenario. Then R-parity violating supersymmetry is apparently making the lightest supersymmetric particle unstable. However, the decaying dark matters may have their lifetime long enough for the age of the universe, and gravitino and axino dark matters can still be consistent with R-parity or lepton number violation in nature, whereby the gravitino or the axino can decay into a neutrino and a photon. So such scenarios, they are unorthodox scenarios of dark matter, but who knows, the answer may be lying there in view of the fact that we are not getting any unanimous answer wherever we are getting some excess. Asymmetric dark matter is something that is particularly mention-worthy this way. We heard about it in the talk by Paolo Gondola, but this is a concept which was used earlier in connection with mirror matter and the dark matter as a technibarian, going back all the way up to 1970s, and it is still a potent issue. This is where a dark sector has a dark matter chi and its conjugate chi bar having an asymmetric population where after their annihilation, one between them is left. And if you make a very simple assumption that chis and baryons have the same population to start with, you have this kind of a mass ratio between them favoring relatively light dark matter candidates. Now, asymmetry between a dark matter candidate and its conjugate may arise through a number of mechanisms about which we have heard a little bit, like out of equilibrium decays of heavy particles, Affleck-Dye mechanism, first order phase transition as in baryogenesis, asymmetric freeze out or freeze in, and also the violation of the Sakharov conditions through primordial CPT violation, which has kind of died out at a later stage. The curiosity here is the fact that there is a striking parallel in the asymmetric dark matter scenario between the emergence of a residual dark matter density and the emergence of a residual baryon number in the universe. So this leads to a very deep question as to whether the dark matter issue and the issue of baryon asymmetry of the universe are connected to each other. And I think all of us could give our life if we can understand this issue. Now, all these points taken care of, one has to admit that the flavor problem continues to bug us. That's why I say this disturbing flavor, we always have to put up with them. Strictly speaking, there is no experimental crisis in having an assortment of flavors as far as the standard model is concerned. Nor there is any naturalness problem in the fermion mass hierarchy in the 't-Hooft'ian sense. However, their occurrence, this flavor pattern, together with this remarkable feat of anomaly cancellation, smacks of a grand design. But the grand design apparently is in what the standard model is handing out to us, but where no clue is offered as to the dynamics which generates this design. It is also a disturbing issue as to why the number of families on which we are setting our limits from precision electroweak observables as well, that is just enough, the maximum number allowed, is to cause CP violation. But the single phase that emerges thereby is inadequate to explain baryon asymmetry. In my view, the whole issue in flavor physics may have something to shed light on this question. So the whole point is whether the grand design that we see in the flavor pattern actually has within it concealed a grander design, something that we must understand sooner or later. Invariably, I come back to SUSY. As some people have said, supersymmetry, when it was given a lot of importance in the community, probably was treated with a little bit of excess fervor. And now that it is being denounced and dismissed, that is also being done with an excessive amount of vengeance. Probably it is too early to dismiss it, in spite of the stringent limits, because possibilities are practically infinite-fold. One of the things that can be said more strongly against SUSY is that the possibilities are infinite-fold. However, the most serious objection that is coming in is that with mass limits going up at LHC, supersymmetry does not emerge anymore as a naturalness problem. What I want to emphasize here is that the issue of naturalness, including the criteria of naturalness in variables like this, depends to a large extent on one's personal metaphysics. You have a worldview set up about naturalness, and we are having everything pitted against that setup, something which may not be the right thing to do. Besides, whether naturalness problem solution is the most important merit of SUSY is something that may be contended at least. However, if at all one has to investigate SUSY, the issue that one may want to investigate or probe seriously is why we have to do so much gymnastics in the minimal supersymmetric standard model to fit the Higgs boson mass. We have to make assumptions about stock masses. We have to make assumptions about trilinear supersymmetry breaking term. We have to make assumptions about the so-called mu parameter, which quite enigmatically is a supersymmetry invariant parameter, but is from electroweak symmetry breaking conditions, is designed to have a value of the same order as the supersymmetry breaking parameters, something which, in spite of this Giudice-Messiero mechanism and so on, we don't have any very clear-cut guideline. So this parameter has to be tuned to high values in order to fit MH. So why do we have to do so? Is that a signal that if supersymmetry works, it must not work as an MSSM scenario? Is something which is not decidedly known, and I think we would do well to know it. On the positive side, of course, I think my personal vote for SUSY as a dark matter scenario is that it offers a dark matter candidate modulo a Z2 symmetry in the least artificial manner. Then, of course, quadratic divergence cancellation to all orders is a good achievement, and so is the better achievement of grand unification of the couplings. And more importantly, in supersymmetry, as Saurav emphasized in his talk, you may have neutrino mass generation mechanisms of all kinds. Delta L equal to 0 neutrino mass generation mechanism, delta L equal to 1 terms in the Lagrangian, as well as the conventional delta L equal to 2. So in all possible ways, supersymmetry can support mass generation mechanisms and hold them up even in the ultraviolet end is definitely a merit of supersymmetry, which we will do well to investigate with greater vigor. And next, thanks to supergravity and umpteen other scenarios, supersymmetry gives us an avenue to ultraviolet completion leading to the Planck scale, immediately raising hopes of unifying gravity into the fold and integrating gravity into our fold, and also opening up at least some ways of thinking or probing the dark energy problem. But the question is whether we are far too committed to certain prototypes in our discussion and investigation of supersymmetry, and whether we need to break away from the prototype in order to place ourselves on a dais where our views will be more balanced. From all that we see and from what nature has taught us so far, high-scale scenarios with grand deserts may not be that viable. That is to say, supergravity-like theory where supersymmetry is broken at the gut scale or the Planck scale and that almost by a divine intervention is handed out to us at the electroweak scale is probably far too idealistic a point of view, which real nature may not support. However, step-by-step ultraviolet completion through many intermediate steps may be alternate ways of looking at supersymmetry and supersymmetry breaking. Grand unification, we have heard about that already, is of course, according to certain physicists, is indicated by the particle contents of the standard model itself. They somehow, again, by a sort of divine dispensation, display gut multiplets, and it is very unlikely. I mean, I'm not saying I support this view, but people have made this argument. It's very unlikely that this indication is totally misleading. So, grand unification remains an area of interest, although one does not know how to experimentally verify or distinguish between various possibilities. Also, one may think whether the imperfect convergence of the coupling constants and their subsequent resolution by putting up the supersymmetry breaking scale at the TeV order, whether that is an infallible way or only way of doing it, or whether there are alternatives to supersymmetry in achieving grand unification and making the coupling constants meet. Left-right symmetry has been discussed in several talks in this meeting. This not only has an aesthetic appeal in sort of resolving the question as to why must God play dice with his left hand only. Over and above that, if you look at it, left-right symmetry kind of suggests a bottom-up approach to grand unification. If there are intermediate scales, and fortunately for us, some scale at low level. Then, of course, in the neutrino sector, left-right symmetry provides new guidelines. Apart from the conventional neutrino mass generation mechanisms which come that way, it also gives us possibilities which are exciting, like relating the Dirac and Majorana neutrino mass matrices in a seesaw framework. This itself is a very, very interesting possibility, as has been pursued by Jose Valle and some of his friends. Incidentally, I am not showing any reference deliberately, but this possibility may not be, may look the way it has been presented in the recent literature may be somewhat artificial, but I somehow strongly suspect that with necessary changes, they have a lot of promise in them. However, the question may arise as to whether we are being unnecessarily hopeful by saying if this aesthetic or bottom-up to gut type things really allows us to keep left-right symmetry in our basket, what is the justification in expecting that left-right symmetry will be broken near about or below the TeV scale so that we can see? The question is, if it is not, can an effective field theory approach allow us to predict signatures at colliders which gives us some kind of smoking gun signals of left-right symmetry if it is not too far high above the scale or mass energy scale accessible to our current day and immediately future colliders. TeV-scale signatures of extra dimensions are of course something that has enthralled all of us starting from the late 1990s. However, it is my personal, maybe incorrect conclusion that it is maybe difficult to sustain motivation on scenarios which have flat extra dimensions. In contrast, warp geometry continues to be a promising proposition. However, this promise probably will be held at high esteem if resonances are at least hinted in high luminosity LHC. That is to say, even if we don't see the bumps in our hunt, you can see the tails of the bumps and it is reflected in some observable or other. There have been other ancillary consequences of warped extra dimensions. For example, the consequences of the torsion of space-time geometry may be in the form of curvature, thanks to Mr. Einstein, but it can equally well be in the form of torsion, and torsion can be in several scenarios sort of theoretically formulated in terms of antisymmetric rank 2 tensor fields like Karl-Raman fields and so on. If you have warp geometry scenarios with graviton as well as torsion in the bulk, then on compactification, thanks to the tensor structure, it can be shown that in 4-dimensional geometry, graviton coupling to matter goes as 1 over mp, massless graviton, but torsion modes, low-lying modes, coupling to matter is diluted much more by an exponential factor, and therefore an explanation is offered as to why our 4-dimensional universe and its evolution is largely influenced by curvature rather than torsion. And there are other issues, theoretical as well as phenomenological, which may continue to worry us as far as extra-dimensional theories are concerned. I think I won't go beyond your limit, Dilip, after all. So finally, a few remarks to make. In case the direct detection of new physics remains elusive, as we are all fearing, seeing no new results in LHC, probably undue fear, but still, effective field theory approach will continue to be an important tool. So probably all of us will be sooner or later forced to pay serious attention and learn to use effective field theories with all their ramifications if we want to look for new physics beyond the reach of whatever our experiments can find this out. Then I have not spoken about the strong interaction sector because I have not worked seriously in that sector. However, one must admit that here, however much the sophistication of the perturbative calculation tools have done, it should be a very, very worrisome thing, almost stealing our sleep, when we have to depend on semi-empirical approach wherever we come to the infrared end of the strong interaction sector, be it in the part on distribution functions or in the fragmentations, where we are seriously talking about jet substructures, jet algorithms and so on. All this has to be in the semi-empirical mode, since there we have been completely stonewalled by nature in understanding how quarks are confined. So I think over and above the theoretical issues, this is, in my view, the biggest challenge to us, even if we understand electroweak physics and new physics in that sector better. And a billion-dollar question at the end, are we thinking of new physics all in the wrong direction? That's why we have spent times in formulating beyond standard scenarios, and according to one physicist, Paul Lengaker, who said in a meeting where I don't recall, about 25 years back, that papers which come out in propagating new physics and new models can be very good candidates, the bulk of them, candidates for the missing mass of the universe. Not that we felt terribly happy being model builders ourselves, but is it really true that we have built model and model after model and model beyond models and models within models? Because we have all been biased in a completely different or kind of conditioned in a way which is probably detrimental to our seeing the truth which is lying in front of us. We will never know. Data will tell us. Experiment is the final guideline. So the person who is speaking about me, after me, will probably bring in candles in front of all of us. It's not me, huh? So maybe we'll learn, but probably in trying to learn about what should be our paths in the theoretical approach, we have to depend on data. So in understanding data, whatever theory we have to do has to be done correctly, over and above the very ambitious, eloquently formulated, and aesthetically appealing models that we have been talking about. Therefore, one recommendation is to quote a poem: build today, then strong and sure, with a firm and ample base, and ascending and secure, shall tomorrow find its place. Here, we of course have a firm and ample base, the platform that I referred to at the beginning of my talk, but then We are feeling secure with that base, although dissatisfied. But then the question is that of ascending. We have to ascend. There may be paths of ascent about which we are not sure. And that path, of course, we have formulated many paths, but probably we need to see more here, thanks to experiments and thanks to our inner voice. Thank you. For everybody, I mean, as I said, most of what I said I don't understand in detail, so others have to answer my question. Yeah. Kaushik.
And then at some point, it let's say starts hit this neutrino bound. Let's say the direct detection dark matter. Now, would you be at what point?
No, Kaushik, the problem is that suppose it's not the neutralino dark matter that we are talking about.
Yes.
Suppose it's an axino and a gravitino dark matter. A gravitino dark matter at keV scale down to up to 0.2 keV, if I'm correct, is consistent with everything. But it won't be amenable to detection in a collider. Gravitino coming and scattered as a gravitino, that Feynman diagram doesn't exist. Gravitino Z type thing.
So everything would go, I mean, probably that's the question.
It's very difficult to rule out in view of that. On the other hand, it provides the right relic density and it will elude experimental detection in detectors. No go again. We would have been very happy had no Higgs been seen up to 150 GeV or nearly 200 GeV. But alas, that hasn't happened and the Higgs has appeared.